As I mentioned earlier, I'm a scientist working at Children's Hospital here in Boston, and I mostly focus on spinal cord imaging and myelitis in children. So I chose to talk to you today about myelin specifically, because I think there's an overall goal in the field, in the community on myelin repair. So I think it would be good to see where imaging can help us in terms of myelin imaging. So we all agree that MRI is of great value when diagnosing myelitis. Usually the findings are, as Dr. Benson mentioned this morning, are come in a sort of a changes in signal. It's like a bright signal. You see what they call, so as you can see in the image on your right, where the arrow points at, that's where a lesion is. It's usually sensitive to disease pathology. It correlates well with clinical status of the patients, and it can also be used to monitor disease progression. However, there are things that MRI does not tell us. One is the microstructure of the spinal cord, where the lesion stops exactly, where it starts, what is happening above and below the lesion, and also, most importantly, are these signal changes due to damage to the axons or damage to the myelin? There are, so there's a great interest in the imaging field on myelin and what techniques are there to quantify myelin loss. One of them, so there are plenty of techniques. The one I chose to talk to you about today is called magnetization transfer imaging. And this technique has been around for decades, but it's not used in myelitis. I know the last thing you want to do on a Saturday afternoon is a lesson in anatomy or MR physics, so we'll keep this very short. You all know what a neuron is by now. It's made of a cell body, axon, and myelin. Myelin is made of 80% lipids or fats. It also has some water content in there. And this is how I like to look at myelin. And these lipid molecules and water molecules, they talk to each other. They interact. They exchange energy or magnetization. And using MRI, we can estimate that transfer. So magnetization transfer imaging is MRI-based, and when that transfer is lower, it means that there are less lipids. And when we do this analysis, we get one number. It's called magnetization transfer ratio, or MTR. And anytime we see low MTR, we say, okay, there was loss in myelin. It's used extensively in MS and also in brain studies, but as I mentioned, not in myelitis. This is not, I like to always mention this because these advanced MRI techniques are not used clinically. We're not trying to replace conventional MRI. We think that it adds value to existing clinical protocols. So it may be a good supplement to conventional MRI. And to give you an idea on on the research going on right now in spinal cord MTI, I did a small search on PubMed. Do you guys know what PubMed is? Some hands. It's a database of publications, scientific publications, established by the NIH. And so I went there just to see how many publications are there in spinal cord MTI. Well, but first I wanted to see brain and MTI, and there were about 370 papers as of last week in the last 10 years. Next, I looked at MTI and MS, and there were about 174 papers. MTI and spinal cord, very, very tiny number. And then MTI and myelitis, there were only 2 papers as of last week. So this was sort of the motivation behind the work we're doing at Boston Children's Hospital. Some of my colleagues are actually here in the audience. You all know Dr. Benson and Dr. Gorman. And we started this study back in 2015, and we recruited about 20 patients since then. And I have some preliminary results to share with you today. The first thing we did was scan all the patients to get their MTR values. So in this graph so we have MTR values and then spinal cord levels. And this is just to give you an idea on what MTR looks like. And then to make sure that our technique is actually reliable, we scanned everybody twice. And we got pretty good results in our reproducibility. ICC, the 0.97 stands for intra-class correlation coefficient, which is a measure of how well your technique is between scan 1 and scan 2. It goes from 0 to 1, 1 being excellent reproducibility. So we actually got close to excellent reproducibility. And these are children, myelitis. I think one of the speakers earlier mentioned how challenging it is to scan kids without sedation, but we do a pretty good job here at Children's Hospital. Next is actually some of my really cool results. So here we looked at the patients, we compared lesion versus what's going on above the lesion and what's going on below the lesion. When I say lesion, it means where MRI was positive, where radiologists, neurologists said there is a lesion. And this is, so we have MTR of 43.11. We did an average of above the lesion, which means MRI negative, which means the report says there's no injury, right? And then we looked at below the lesion, and also, and these are the values we saw. So now, you're all gonna help me analyze the data, okay? So everybody's gonna be scientists for a minute. Let's say we compare lesion versus above lesion. Do you think we should see differences or no? Statistically speaking. We should, right? Okay. Because one is negative, one is positive. So, yes, there were statistical significant differences, and P is less than 0.5 means there are differences. Next, lesion versus below lesion. Do you think there should be differences in MTR values when we look at MRI positive lesion versus MRI negative below lesion? Right? Yes? No differences. How about above lesion versus below lesion? These are both MRI negative. Do you think they should be different or they should be similar? They should be similar, right? But they're actually different. Okay. So this was pretty interesting to us because we did not expect to see anything happening below the lesion because this is MRI negative. So for once, we think that MTR probably was able to pick up things that MRI was not able to pick up, and that's why we saw differences. And now we're looking into, and that's why I said preliminary results. We still have a lot of work to do. Now we're looking at comparing these data to data from other myelin imaging techniques to see if they too will show similar results. But it's really interesting to. It was eye-opening, I must say. This is actually I think my last slide. But if you leave today with more questions than answers after my talk, then I did my job right. So these techniques are pretty promising, but we still need a lot of experimental evidence to make sure that the changes we see are actually changes due to myelin loss, and another question we're interested in looking at is, can we differentiate between different etiologies of MS? Because we're recruiting, the data I showed are from AFM, NMO, TM patients. We just don't have the sample size large enough to be able to discriminate between all these etiologies and see whether advanced imaging can help us discriminate between different etiologies. The next question we're interested in is, can we differentiate between disease phases, so acute versus subacute versus chronic? Because I think that if we see differences between acute and subacute, maybe the changes are due to inflammation versus loss of myelin versus what happens later on, which is probably axonal loss. And there are imaging techniques out there that have, that promising enough to help us answer these questions. And we have the data to be able to answer these questions. And then my favorite is, from what Dr. Greenberg was mentioning earlier, can we use these imaging techniques to monitor remyelination? If our overall goal is myelin repair, can MTR, for example, be a predictor for remyelination? So that's what I have for you today. I know it was very quick, but it was an update on this research study that we have been doing here at Boston Children's Hospital, and that we are also moving to include adults as well in an upcoming study. And with that, I would like to thank my teammates, my colleagues in neurology, Dr. Benson, Dr. Gorman, who are here with us in the audience, my students, you met Lorraine, and of course the NIH for their funding in the past 4 years. And this is our email address, so feel free to email us with questions or comments or anything you may have. And that's it. That's all I have for you today. Thank you for your attention. And this talk had 2 parts. I forgot to mention that in the beginning. I was part 1, and part 2 will be handed over to my colleague and very good friend, Dr. Robert Barry from Mass General Hospital, who is going to talk to us about the research they're doing over there. And this is your first RNDS, right? Okay, good.
Well, thank you very much, Nadia, and thank you for the organizers for inviting me here today. In the words of Monty Python, and now for something completely different. I'm basically going to talk a lot about how these images that you've been seeing today might be formed, what some of the problems might be with their interpretation, how we might make them better for the future. So MRI. Anyone in the room's been in an MRI before, had an MRI? A whole bunch of hands up. Okay, good. Now hold your hands up. Do you know what field strength you had the MRI at? No? Yeah, so nobody. One person? 3T. Thank you. Thank you very much. So this is the thing I want to tell you about. MRI stands for magnetic resonance imaging. But if you take one thing away from my talk today, I want you to remember the strength of the magnetic field matters. And I'll show you why. So some people are kind of scared of magnetic fields. Well, don't be. You're in one right now. The Earth has a magnetic field. You were born in a magnetic field. We live our lives in a magnetic field. The difference is the magnetic field in one of these MRIs is much, much stronger. How much stronger? Well, basically a conventional MRI, conventional being one that you'll see at a hospital in almost any city, is somewhere in the neighborhood of 30 to 60,000 times the Earth's magnetic field. Okay, so that's a lot. Research scanners, some of the ones that I play at, are something in the tune of 140,000 times the Earth's magnetic field. And you might say, wow, those are both big numbers, does it matter? Well, if you drop like the last 3 zeros and I say, does it make a difference whether or not you're driving 30 to 60 miles per hour or if you're driving at 140 miles per hour? Yes, it makes a big difference. So the difference between these numbers actually enables you to potentially see more that you could not see at lower fields, and I'll show you a couple of examples. So basically, what you can see in the body depends entirely on the magnetic field. Now, from the research point of view, most of the research, for better or for worse, is done on the brain. And we are now talking about research on the spinal cord. Now, obviously, there's a lot of diseases that affect the spinal cord, myelitis being one of them. And so we want to try to refocus and develop methods and efforts to better study the spinal cord in many diseases, especially myelitis. So if I were to kind of make a cartoon plot here, if we say anatomy of interest is up here, field strength is this way, the further away from that little corner I get, the harder it is to do the imaging. All right? So I can say that on this plot, brain is somewhere in the middle because we know how to image the brain. We're pretty good at it. And the spinal cord is just more difficult. It just is. So the first thing, which I think we all kind of inherently know, but maybe to articulate, is that it is an order of magnitude smaller than the brain. So if we overlay the spinal cord on the brain, that little red dot is basically what we get. So it's actually really hard to image the spinal cord because it is a very small structure. And especially so when you kind of look at these things and taking a look at just these, like, the butterfly of the gray matter. So to use the previous terminology from Dr. Greenberg, these are like, the part that has the type 2 wires. So this is like looking at your pinky finger, and I want to look at the pinky nail, and then take a look at the half of your pinky nail. I mean, these are really, really small structures, and this is on the cutting edge of what you can do with an MRI. Additionally, it's really, really long. We're taking a look at the gray matter horns, about 1 millimeter. The cross-sectional area is a diameter is about 1 centimeter, and then it's about 1 meter long. So it's actually very hard to look at the whole cord. We kind of have to typically take a look at little sections and use it as a proxy for what goes on. Additionally, from the MR physics point of view, movement and MRI don't get along. For those people that have been in MRI, the technologist, I'm sure about 20 times told you, please stay still. The reason is any movement completely messes up the image. Now, even if you're staying still, of course, you have the movement of your tongue, throat, heart, lungs, and everything else that's squishy that moves. Oh, don't forget, there's pulsating blood, lymphatic fluids, and cerebrospinal fluids. So basically, even if you're not moving, your body is moving. You're alive. As a result, it's actually quite difficult to acquire these images many times. So at 3 Tesla, which is a very standard clinical field strength, it's hard. But then at 7 Tesla, this is that almost 200,000 times the Earth's magnetic field that I'm playing at, it's even more hard. It's more difficult. These problems are exacerbated by the higher fields. So if you're to say, well, why would we want to do 7 Tesla? Well, basically, the images can be much, much better. Here an example in the brain, you can have higher contrast for the same scan time and resolution. Taking a look at very small midbrain structures, striations on the pons, cerebellum, microvascular structures. These are very, very, very small things, and they're of millimeters, and you can actually start to see them very clearly at 7 Tesla. Now, midbrain, look at this gorgeous image. These are things that you just cannot typically see at a conventional clinical field strength. Now, if we want to go back to this plot and say, well, I want to talk to you for a couple of minutes about 7 Tesla spinal cord imaging, you kind of see that where this might fall. And if you're having flashbacks of like grade 9 trig, your intuition is correct here. It's not just like the same. This is actually kind of like doubly so, trying to combine these two things together. But this is what you can do when you do this. Remember those fuzzy pictures that previous presenters showed you, and they kind of had to say like, well, this thing in the middle, this fuzzy blob is a spinal cord. At higher fields, you can not only clearly resolve the spinal cord, but you can actually start to see structures within the white matter, structures within the gray matter. You actually start to see the little prongs on the ventral horns. That's the top part there. So this is phenomenal. Now, unfortunately, there's only a few of these centers in the world. I'll summarize that in a minute. In multiple sclerosis, as an example, what people have done is looked at lesions in the spinal cord at 7 Tesla. Now, this was actually a very exciting study because what the people did was they had a cohort of patients with relapsing remitting MS, and they scanned them at 3 Tesla, and then they scanned the exact same cohort at 7 Tesla. And what they found was that at 7 Tesla, at this higher field strength, you could actually see 50% more lesions in the cord. So let me just kind of reemphasize this. This means that what you can see pathologically, which might be clinically relevant, depends upon the field strength you use. And if you can't see it, you can't treat it. So here's examples of lesions in the cord, both on the sagittal and axial views in both white and gray matter. And as well, we've been talking about anatomical imaging. What is the pretty picture of the cord? What can the picture tell us in terms of hyperintensities? It's brighter when you don't expect it to be, or hypointensities. It's darker when you don't expect it to be. We've also been taking a look at functional imaging. This kind of means, with regards to the previous terminology, like how can, the wire 2 in the left part talk to wire 2 in the right part? there's projections between the two. So you can actually take a look perhaps at investigating biomarkers for how when the demyelination happens, when there's breakdown in the white matter, how can it start to disrupt the connections within the spinal cord. So this is extremely new stuff. It was a very long development of the methods, and there's only a couple papers in the world that have now looked at this. However, I'm very pleased to tell you that as of a couple months ago, we were the first group to show that at 7 Tesla, you could actually detect changes in these signaling patterns in the spinal cord between patients with relapsing remitting in areas that do not have and have lesions. So this is the first step towards actually doing something and taking a look, not only, does the anatomy change, but can you actually see in real time perhaps evidence of functional lesions or active lesions? And this opens up a whole new possibility of potentially studying the cord in not just MS, but in myelitis and other neurological diseases. So in summary, I'd just like you to get the understanding that the field strength matters. Now, one of the disadvantages of everything I've told you about is that there are about 77 Tesla systems in the world. That's not a lot. And most of them have actually been installed in the last few years. So it's actually showing a resurgence in this area. Now, the exciting thing for the people in this room is that there are currently 2 in Boston. MGH got the second one in the world back in about 2001, and Brigham and Women's just got theirs a couple months ago. Additionally, MGH is getting its second 7T in a couple months, which means that early next year, we'll have 3 operational 7 Teslas in one city, whereas the rest of the world has the other 67 or so. So this is phenomenal. Additionally, FDA has granted 510K approval for the Siemens 7T Magnetom scanner, which means that it now opens up the door for potential clinical uses of the 7 Tesla, which has not previously been seen. So this is another game changer as of exactly a year ago. So in summary, studying the structure and the function of the spinal cord is a very recent development. It's very exciting. Technically, I want to kind of convey that it's also very, very difficult. Like I'm an engineer, so much of my day is spent thinking about these images. How can I make them better? How can I potentially make them more diagnostically useful? And MRI is not an easy field. And when you do it at higher fields, it is very challenging, but what it can provide to you that might not be possible at lower fields, it cannot be ignored. It's definitely something that is very important. We've just started working on multiple sclerosis, and importantly, this technology has not yet been applied to patients with myelitis. So this is a completely wide open opportunity. We have phenomenal imaging expertise at MGH and Brigham's. We have phenomenal clinicians and radiologists who do work in myelitis. All we need to do is start, putting the two together and talking and seeing how we can start to develop next generation technologies to start to study myelitis in new ways possible at 7 Tesla. Thank you very much for your attention.